Welcome to lecture 16 of analog integrated circuit design. We were in the process of designing op amps at the level of control sources or transconductors and improving their performance. That is, in particular, we want to get higher and higher DC gains. We want to figure out how to make these op amps with higher DC gains, while of course maintaining stability of the feedback loops. We already saw some techniques which gave us the 2-stage and 3-stage Miller compensated op amps. Now we will look at another technique to increase the DC gain starting from the original integrator topology. Okay. I will use the standard op amp amplifier as an example. If I apply a constant input Vi and the ratio of resistors is k minus 1, the output is supposed to be kVi, but what we really get is kVi by 1 plus k divided by A naught, where A naught is the DC gain of the op amp. And the voltage here should have been Vi itself, that is, the two voltages being compared by the op amp should be the same after it reaches steady state, but they are not, and this voltage is smaller than Vi. It is equal to Vi by 1 plus k by A naught. It is close to Vi, but not exactly equal to Vi. Now let me use the op amp that we have been discussing, the simplest op amp. It has a transconductor which has an output conductance G01, and that is loaded by a capacitor. And just for simplicity, I will insert a buffer here, but this is not really necessary. Okay. Later when we implement op amps, we see that we do not always implement the buffer. Now this we know has a DC gain A naught equals Gm1 by Go1. Okay. So whatever I described on the left side will happen here, and the voltage here will be slightly smaller than Vi. Okay. Now we will try to fix this situation by going back to the idea, the original idea of negative feedback. What was that? First of all, in steady state, what happens is that there has to be some current flowing through Go1, so that there is a certain voltage that is supported here. The actual output voltage turns out to be kVi by 1 plus k by A naught, and it is the same here. And if this voltage has to be at this node, some current has to be flowing through Go1. Okay. And that current comes out of this transconductor Gm1. Now if a current has to come out of this transconductor, these two voltages have to be different from each other, because after all, if they were the same, the current output of the transconductor would be 0. Okay. So to fix this, what we must do is to provide the current that flows through Go1 from a different path. Okay. So that the transconductor itself does not have to provide an output current. So its input difference will be 0. Okay. And how much should this current be? We do not know exactly what it will be. Okay. I mean, it is not easy to calculate, because these parameters Gm1 and Go1, all these things are varying, and what we would like is for this current to automatically set itself to a value such that the difference between these 2 points becomes 0. Okay. And that is exactly what the original negative feedback idea was doing, that is, you want to control some quantity based on the error between some desired quantity and some controllable quantity. Okay. So how did we do that? We took the difference between the desired and actual values, and we integrated that over time, and in this case this should be a current, the integrated quantity, the output should be a current which is related to the integral of this difference. So what happens is that after a while, for it to reach steady state, for this current to be steady, the input to the integrator has to be 0, which means that this and that will have to be the same as each other. In this condition, what happens is the current that has to go through Go1 will be provided by this path, and nothing will be provided by Gm1. Okay. So its input difference can be 0. Okay. So, that is the basic principle. Now, how do we implement this integrator and this differencing and so on? Exactly the way we have been doing it all along. First of all, we have to make an integrator and also the output of that has to be a current. So, to integrate the difference between these two voltages, what I do is use a transconductor loaded by a capacitor. Okay. Let me call this C1, I will call this C2. And finally, what I want to inject here is a current. So, I take this voltage and convert it to a current using another transconductor. Okay. So, this is all I have. Essentially, the block above, what it is doing is to take the difference between these two, integrate it, convert the integral to a current and feeding it into this. If everything works perfectly, then the difference between these two voltages has to be 0, okay, in steady state. Also, keep in mind that we said that the circuit below already reaches steady state, and when it has reached steady state, the other controller appears into picture. Okay. In reality, both are working simultaneously. What we really mean is that the second circuit, this integrator and the transconductor, this signal path operates more slowly compared to this particular circuit. This is so that essentially what this transconductor here should be measuring is the steady state error between these two, and it is providing a compensating current which is related to the integral of that steady state error. Okay. So, this idea is looks fine, and you can see that in steady state there will be no current flowing through this capacitor C2. So, these two voltages will be equal to each other, but of course, the catch is that we said this transconductor will have some output conductance which is not 0. Similarly, these transconductors will also have output conductances which are not zeros. Okay. So, we will inevitably have that one. So, let me call this GM2 and that will be GO2. Similarly, if this is GM3, it will have its own output conductance GO3. Okay. So, it is one thing to get an idea, and the next thing is to put down all the non-ideal effects that come in while implementing the idea and see if it really works. Okay. So, now my op amp, I can call this entire complicated beast my op amp. Okay. Because whenever I make an op amp negative feedback circuit, I am going to use the whole thing, right. I will use this, this was my original op amp, but to fix the steady state error of this I need all of this stuff. So, I am going to use the whole thing. So, that is my new op amp. Okay. I may or may not use the buffer as usual. So, if I redraw the op amp by itself, I will have the original part and I have the part that I have added. Okay. And this will also have some GO3, this is GM3, and there could be a C3 as well. Okay. This is the input to the op amp and that is the output of the op amp. Okay. Now, as usual I could use a buffer after this, but I will assume that I do not, because normally in CMOS circuits we tend not to use it, although it is very much possible. And finally, you see that this GO3 and GO1 are in parallel, and it will also be in parallel with any load resistance that you connect. Similarly, C3 and C1 are in parallel, and they will also be in parallel with any load capacitance that you connect. So, I will combine all these things into a single load conductance GL and a load capacitance CL. Okay. So, this is my new op amp, and remember our goal was to improve the DC gain of the op amp. Now, will this have higher DC gain? So, the first thing is we can analyze the DC gain very easily as usual by opening the capacitors. And what will be the DC gain of this? If I apply VE here, the voltage that appears there will be GM2 by GO2 times VE. Okay. The current that flows here will be GM1 times VE, and the current that flows here is GM3 GM2 by GO2 times VE. So, the output voltage at DC will be nothing but GM1 plus GM3 GM2 by GO2, the whole thing divided by GL. Okay. And this is the DC gain. Now, it is very easy to see that this was the original DC gain and we have added this much to it, and in fact, what we have added is likely to be much more than the original DC gain, because it essentially is the DC gain of 2 stages. In fact, it is a similar number to what you got from the 2-stage Miller compensated op amp. Okay. The 2-stage Miller compensated op amp, after we implemented all the stages using transconductors, had this form. It was product of 2 GM by GOs. Okay. Similarly, here we have that, we also have this one added, but GM3 by GO2 is likely to be a large number. So, most of the DC gain is provided by this path, whereas this provides a modest amount of DC gain. Okay. Whereas this is, performs the function of integration that is required inside the op amp, the GM1 and CL together, and this provides the other path provides the DC gain. Okay. So, our idea has worked and we have got an op amp with a higher DC gain. Now, we also have other capacitors here, which means there could be more poles and zeros. We do have to analyze that and see if stability is okay. Okay. So, this is the DC gain A naught, and roughly speaking it is like the DC gain of a cascade of 2 stages, which is the 2 stages on top here. Okay. And because we have 2 stages here and the single stage going from the input to the output of that, that is usually known as feed forward, and this is known as a feed forward op amp, okay, or sometimes feed forward compensated op amp. Now, the term frequency compensation is the term that is commonly used to get this behavior of integration in the op amp. I have earlier said that the op amp has to behave as an integrator, at least in some crucial range of frequencies. Whatever you do in the circuit domain to get that integrating behavior is called frequency compensation. We have not used that term often, but that is what it is. I will explain later what it means in different contexts as well. Okay. So, in this particular case, this transconductor GM1 together with CL provides that integrating behavior, and that is feeding forward across the 2 stages that we use to get a high DC gain. So, it is called a feed forward compensated op amp. Okay. Now, the next thing we have to find out is the frequency dependent behavior, okay, V naught of S by V of S. Remember, this is what we did for the Miller compensated op amp and other op amps that we discussed earlier. Okay. And again, that is quite easy. All I have to do is recognize that the voltage at the output of the first stage is not merely GM2 by GO2, but GM2 by GO2 plus SC2 times VE. Okay. We also have the capacitor. So, that voltage will be GM2 by GO2 plus SC2 times VE. Okay. So, the current output of GM3 will be GO2 plus SC2, it will have GO2 plus SC2 in the denominator, and the current output of GM1 will be GM1 times VE. The two terms get added together. So, V naught of S by VE of S turns out to be GM1 plus GM2 GM3 by GO2 plus SC2, and this whole thing will be divided by the load admittance, which is GL plus SCL. Okay. Okay. So, the gain, the transfer function of the op amp can be expressed as a sum of this first order term, which in fact you recognize that this is what we would have with the simple single stage op amp, plus this part due to the two stages that we have across them. Okay. Now, this can also be written as okay. Now, this you can see is of the form some DC gain times a 0 divided by times a term containing a 0 divided by terms containing 2 poles. Okay. Here the pole is at minus P1 and P1 itself will be equal to GL by CL, and the other pole is at minus P2 and P2 will be equal to GO2 by C2, and the 0 Z1 will be at GM1 GO2 plus GM2 GM3 divided by GM1 SC2. Okay. Because we expect GO, the output conductance, to be much smaller than the transconductances, this can be approximated to GM2 GM3 by GM1 times C2. Okay. This is not SC2, but merely C2. So, we have a transfer function with 2 poles and a 0, and of course, the poles are in the left half plane and the 0 also is in the left half plane. Okay. Now, we have to see what the effect of this on the stability is. So, we can do that by drawing Bode and Nyquist plots. Let me draw the Bode plot here, and it is easiest to use the form where we had GM1 by GL plus SCL plus GM2 GM3 by GO2 plus SC2 times GL plus SCL. Okay. Now, the first of these is a first order transfer function with a DC gain of GM1 by GL, okay, and it has a pole at GL by CL, and it rolls off at 20 dB per decade after that, and it cuts unity gain at, if you recall, it will be GM1 by CL. Okay. For reasonably large DC gains, the unity gain frequency will be equal to the DC gain times the pole frequency. Okay. The second term will have a DC gain which is higher, we expect it to be higher, which is GM2 GM3 by GO2 GL. Okay. And there will be 2 poles. One of the poles will be the same value. The other pole, for drawing this plot, I will assume it to be at a lower frequency. Okay. this is at Go2 by C2, okay. That is the pole corresponding to that term. So, it rolls off at 20 dB per decade, and after that it rolls off at minus 40 dB per decade, okay. This is the magnitude of the gain of the op amp. As I have mentioned before, if the op amp is in unity feedback, the op amp's gain itself is the loop gain, and we can assess stability of a unity feedback amplifier by looking at the gain of the op amp, okay. And what happens when you sum these two? Now, remember that this Bode plot is a logarithmic plot, the y axis is log of the magnitude. So, when you add up two different plots like this, you can simply approximate it by the higher of the two numbers, okay. So, the sum of the plot of the sum of the two will look something like that. Now, this sum will be inaccurate in this area where both have similar magnitude, but when one is much more than the other, you simply follow the higher one to give you the magnitude, okay. So, this is a general thing when you have two functions being added together, and especially when you plot it on a log scale, and you want to plot the sum of the two functions, you simply follow the higher valued function, okay. Now, what happens to the phase? First of all, for drawing the phase, the other form is more convenient, okay. The form that is given by this expression. By the way, it is also very easy to see where the 0 is in this plot, in the magnitude plot. We know that we expect a 0. Now, you see that the slope changed from minus 40 back to minus 20, okay. This part of the curve has minus 20, right. So, the 0 is at that particular frequency. We calculated the value of the 0, it was Gm2 Gm3 by Gm1 times C2 approximately, and that is where it is going to be, okay. Now, what happens to the phase plot? First of all, at low frequencies, as usual, we have a positive real number. So, the phase shift will be 0, okay. That is at some very low frequency, let us say somewhere over here. Now, at the first pole Go2 by C2, we see that it will have a phase shift of 45, and then it goes off to minus 90, that is the contribution of the first pole. The second pole will add another 45 degrees phase at the frequency of the pole, and then the phase shift due to that pole also saturates to minus 90, okay. So, after you pass these two poles, what happens is the phase would shift to minus 180 degrees, okay. Each pole contributes a phase shift of 90 degrees, phase lag of 90 degrees. So, the two poles together will contribute a phase shift of minus 180 degrees or a phase lag of 180 degrees once you go to a frequency that is well beyond both the poles, okay. Then you have the 0, and this 0 is a left half plane 0. So, that creates a phase lead. So, what does it do? At the frequency of the 0, there will be a lead of 45 degrees, and then the phase lead will also saturate to 90 degrees. So, after some frequency, the phase will become approximately minus 90 degrees, okay. The way I have drawn the plot, you can see that at the unity gain frequency, which is Gm1 by Cl, the phase is close to minus 90 degrees. Does not have to be, but it will do something of this sort, that is clear, okay. So, it starts from 0 degrees, then it goes down to minus 180 degrees because of these two poles, then comes back up to minus 90 degrees due to this 0, okay. So, this is the phase response of the op amp. Now, this magnitude and phase response, this Bode plot is quite different from the op-amp Bode plot that you have seen earlier and also what we have discussed in detail. Okay. What did we say earlier? We will have one pole at very low frequencies. In fact, if the op-amp is an integrator, that will be at 0 frequency, and any other poles are 0 should happen after the unity gain frequency of the op-amp. Okay. That is some point corresponding to this one. Now, what do we have? We have 2 poles before the unity gain frequency, but we also have a 0 before the unity gain frequency. So, is this really stable or not? What do you think? Now, to assess this, we have to go back to Nyquist criterion, which is the rigorous way of analyzing stability. Okay. So, once you understand the Nyquist plot of a system corresponding to this, you can do it from the Bode plot directly, but to be able to understand it properly, we have to go to the Nyquist plot. And what is the Nyquist plot? It is the plot of the loop gain, imaginary of part of L versus real part of L, as the frequency is varied from low to high values, from 0 to infinity. Okay. So, in this particular case, what happens? First of all, at very low frequencies, that is some frequency corresponding to this, the loop gain magnitude is very large and the phase shift is 0. So, that means we start from some point here. Okay. So, maybe I will mark it with this point 1, which corresponds to somewhere over here and somewhere over there. So, it starts on the positive real axis, and as you go further, the magnitude keeps on lowering, but the phase becomes more negative, there will be more and more phase lag. Okay. So, this plot spirals inward in some way. Okay. Finally, it goes all the way down to 180 degrees, and remember, the phase shift due to 2 poles will asymptotically reach 180 degrees, it will not be exactly 180 degrees ever. Okay. So, it kind of touches this negative real axis. The magnitude of course is continuously decreasing. So, it is going on inwards towards the origin, and the phase comes back to 90 degrees. So, that means that this curve will finally approach the origin, that is origin simply means that the magnitude is 0, okay, and the phase there is minus 90 degrees. So, that means that it approaches it from the negative imaginary axis. Okay. So, this will be the Nyquist plot of the feed forward op amp if it is connected in unity feedback. Okay. Now, is this stable or unstable? Now, it depends on where the unit circle is. Basically, let us say that the unit circle is here on this plot. Okay. The Nyquist plot enters the unit circle over there, and then the other half of it will be a mirror image okay. It will be something like that. Now, you can see that again there is no encirclement of this particular point, that is this point here is the critical -10 point. You see that the plot kind of goes around it, right, without encircling it in the clockwise direction. We saw that the number of clockwise encirclements equals the number of right half plane poles if the open loop system does not have any right half plane poles to begin with. Okay. So, in this case there is no encirclement, so the system is stable. Okay. System is definitely stable because you can see that because this curve only touches the negative real axis, it will never actually encircle the -10 point. Okay. The most it does is to barely touch the negative real axis. Okay. So, you cannot have a plot that goes around the -10 point ever. right. But let us say the magnitude response looked slightly different from this. I will draw it in a different color. So, let us say it did something of the sort. Okay. Let us say it perhaps started from elsewhere, and again this goes close to the negative real axis, it comes back like that, and then finally it goes to the origin, that is for sure, and the mirror image of that will do that. Again there is no encirclement, but you see that the Nyquist plot enters the unit circle at an angle very close to minus 180 degrees. The original green curve enters the unit circle at this point, which is quite far from minus 180 degrees, and the orange curve enters the unit circle at a point very close to minus 180 degrees. Okay. So, what do you conclude from this? The orange curve has very poor phase margin. Okay. What is phase margin after all? It is the angular separation between this point minus 1 0 and where the Nyquist plot enters the unit circle. Okay. The green curve has a large phase margin which is quite healthy, it will be stable. As I said earlier, we derived conditions for stability, and not only stability, stability margin, that is good behavior without lot of ringing, based on our analysis of systems with ideal delays and low order systems like first order systems and second order systems and so on. And we saw that if you have a large phase margin, you will generally have a step response which does not have ringing. Okay. So, in this particular case, if you enclose this op amp in a unity feedback loop, and if the op amp's transfer function happens to follow this green curve, then there will be no significant ringing, and if it follows this orange curve, you expect that there will be a lot of ringing. Okay. We will confirm this by explicit analysis. In this particular case, we only have 2 poles, this we can analyze explicitly, but in general we can use the phase margin criterion for stability. Now, the way I have drawn this plot, you see that the 0 appears well before the unity gain frequency. So, that means that the phase shift at the unity gain frequency is close to minus 90 degrees. Okay. So, in fact, it is much closer to the green curve than the orange curve. The loop gain corresponding to the orange curve would have been something of this sort. Okay. It would start from some magnitude, let us say it has the same poles, and there will be a 0 which may be little bit before the unity gain frequency or maybe even after. Okay. So, if the orange curve is what represents the op amp's gain, you can see that the phase shift at the unity gain frequency is very far from minus 90 degrees. Okay. So, this kind of an op amp can be stable, we just have to plot the Nyquist plot and make sure that the phase margin is high. But once you understand this phenomenon, you do not have to actually explicitly plot the Nyquist plot, you can ascertain directly from the Bode plot that the phase margin is quite high. Okay. We needed the Nyquist plot because we wanted to make sure that there is no encirclement of the minus 1 0 point, and there is not, and we can see that at this point the way I have drawn the plot, the phase margin is almost 90 degrees, okay, which is quite healthy. But it is possible for it to have a very poor phase margin and become close to instability. Okay. Just like the second order system, this will never become completely unstable, but it can become close to unstable because the Nyquist plot can enter the unit circle at a point very close to minus 180 degrees. Okay. So, what is the criterion for stability on the Bode plot? First of all, we want the phase shift at the unity gain frequency, which is GM1 by CL, okay, to be close to minus 90 degrees. Now, what is the phase shift due to? First of all, before the unity loop gain frequency, there are 2 poles and a 0. The 2 poles will give a net phase shift of minus 180 degrees at high frequencies, and the 0 will give a phase shift of plus 90 degrees at high frequencies. Okay. And what we want? We want a positive phase margin, that is, we want to stay away from minus 180 degrees. So, this clearly means that the 0 has to occur before the unity gain frequency, okay, because if the 0 did occur after the unity gain frequency and you had 2 poles before the unity gain frequency, at the unity gain frequency the phase shift would be very close to minus 180 degrees. Okay. Let me draw it on a different plot. So, let us say this is the magnitude plot and I had something like that. Okay. This is the first pole, second pole and the 0, and this is the magnitude plot, this is the phase plot. In this case the phase would start from here, and because of these two poles in this region of frequencies reach almost minus 180 degrees, and because of the 0 come back to minus 90 degrees. Okay. Now, you can see that the phase margin here is really poor. Okay. The phase shift at the unity gain frequency, this is the unity gain frequency, that is very close to minus 180 degrees. So, it is very poor. Okay. So, this means that in the Nyquist plot, the Nyquist plot will enter the unit circle at an angle close to minus 180 degrees. Okay. So, this kind of plot is simply not admissible. What we would like to have is a plot that looks more like this. The poles can be anywhere, but wherever they are, the 0 has to occur well before the unity gain frequency. Okay. This is the unity gain frequency, perhaps a different plot will make it more clear. This is the gain magnitude, this is the angle, and in this case the angle will be, it again goes almost to minus 180 degrees in this region. Okay. But it comes back to something close to minus 90 degrees by the time the gain drops down to 0 dB. Okay. So, in this case the phase margin is quite large. Okay. And you can very easily see that if you have multiple poles before the unity gain frequency, what happens is the phase goes to minus 180 degrees or beyond that, and the only way for the Nyquist plot to enter the unit circle in the third quadrant is to have also zeros before the unity gain frequency. Okay. In fact, if I have 3 poles before the unity gain frequency, they will contribute a net phase shift of minus 270 degrees, but I want a net phase shift of between minus 90 and minus 180 degrees at the unity gain frequency. So, that means that I also have to have 2 zeros. Okay. So, in fact, the number of poles and zeros before the unity gain frequency should be such that the number of poles minus number of zeros is 1. Okay. Earlier we had articulated the stability criterion differently. In fact, we were only looking at cases where there was a single pole before the unity gain frequency or unity loop gain frequency to be precise, and we could have more poles beyond the unity loop gain frequency, and we said that they should be sufficiently far, sufficiently beyond the unity loop gain frequency. Okay. Now, that was a restrictive case. It is not necessary that we have a single pole before the unity loop gain frequency, we can have multiple poles, but we should also have zeros, so that the phase shift comes back to somewhere between minus 90 degrees and minus 180 degrees. That means that this phase shift can go to high values, but then the Nyquist plot has to enter the unit circle in the third quadrant, that is with a phase shift of minus 90 to minus 180 degrees. So, which in turn means that if you have NP poles before the unity gain frequency, should have NP minus 1 zeros also, so that the phase shift comes back to somewhere between 90 and 180 degrees phase lag. Okay. This will become even more clear when we discuss the 3-stage feed forward op amp, but it is possible to have op amps with multiple poles before the unity loop gain frequency, but they also have to have zeros. Okay. Okay. Both the poles and the 0 must occur before the unity loop gain frequency for stability. Okay. Now, we have not said what is the factor by which the 0 has to be before the unity loop gain frequency. We will work it out, but it is very clear that the 0 has to come before the unity loop gain frequency. Okay. Now, before we analyze the feed forward op amp that we have more rigorously, we can try and make it better, just like we went from 2-stage Miller compensated op amp to 3 stages. We now have a better op amp compared to the single stage op amp, that is the feed forward compensated op amp, and we can kind of use the idea in a recursive fashion. Okay. This is the original idea, to take the difference between these two and integrate it and push a current here, so that the current that has to go into G01 comes from this path and not from GM1. Okay. If it comes from GM1, there has to be a difference between these two, but if it comes from the integrator, there does not have to be a difference between these two. Okay. So, this part we implemented using the simple op amp, that is we took the difference between these two, integrated it, converted the integrated voltage to a current and fed it to the final output. Okay. The integrators themselves are imperfect, but we saw what the effect of those things are. It still works well enough. Okay. Now, this is what is known as a 2-stage feed forward compensated op amp. Okay. Now, to realize this integrator, okay, we can use the 2-stage feed forward compensated op amp instead. We earlier used a single stage op amp, that is, this integrator differencing and integration was formed by this GM2 and this capacitor C2, okay, and that forms a single stage op amp, right. Now, we can use a 2-stage feed forward compensated op amp in its place, because that is a better integrator. Okay. What do we get if we do that? So, let me draw my GM1, G01, C1. Okay. Because of lack of space, I will not show the output resistances of these transconductors, but they are there. Now, this is my 2-stage feed forward compensated op amp, which behaves like an integrator. Now, I have to convert the integrated voltage to a current and feed it to the output. Okay. So, if I call this GM1 and those things. You can now see that at DC all the capacitors are open. So, basically we will have 3 stages in cascade here, 2 stages in cascade through this path and a single stage from the input to the output. Okay. This is the input of the op amp, that is the output. So, the DC gain will be that of mainly due to these 3 stages in cascade. Okay. It is really the product of these 3 DC gains plus the product of these 2 DC gains plus this particular DC gain, but you expect that the product of 3 DC gains will dominate, and that is what will contribute chiefly to the DC gain. Okay. So, just like when we went from 2 stage Miller compensated op amp to 3 stage Miller compensated op amp, we got a higher DC gain. Here also when we go from 2 stage feed forward compensated op amp to a 3 stage feed forward compensated op amp, we will get a better DC gain. Okay. But it needs all this other structure. You can in fact think of this as some counterpart of the 3 stage nested Miller compensated op amp. So, when we want high DC gains, you can go for 3 stages and also feed forward compensated. Okay. And the DC gain will be approximately the cube of DC gain from each stage. Here I am not writing the specific expression. Gm by Go I consider to be the kind of gain that you can get from a single stage. So, Gm by Go cube is the kind of gain that you can get from a cascade of 3 stages, and that is what you get from the 3 stage feed forward compensated op amp. Okay. So, that is it for today. In the next lecture we will look at the Bode and Nyquist plots of the 3 stage feed forward compensated op amp. This is mainly to understand stability when you have multiple poles and zeros before the unity loop gain frequency. Okay. Also for the 2 stage feed forward compensated op amp, we will rigorously evaluate the poles and zeros and see how close the 0 can be to the unity loop gain frequency. Okay. Because we only said that the 0 has to be below the unity loop gain frequency, we have not said how much, that we will do in the next lecture. Thank you.